Hello and welcome to a session on implementation of RTOS, that is real-time operating system. This is Dr. Anita Pujar, Professor in Computer Science and Engineering Department at Walchand Institute of Technology, Solapur. At the end of this session, learners will be able to know about features required for the implementation of real-time operating systems. Prerequisites: the learner should have the basic knowledge of CPU scheduling algorithms used for general purpose operating systems. Let's see the features necessary for implementing the real-time operating system. So there are three features required for the implementation of RTOS. First one is preemptive priority based scheduling. Second one is preemptive kernel. Third one is minimize latency. Note, if a real-time system must be connected to network for some data transfer, then additional feature, that is networking support, is required. That will be the fourth feature for implementing RTOS. For example, suppose a system gathers real-time data and transfers it to a server, then support for the networking, that is TCP/IP protocol stack, is required. Now let's consider the first feature, that is priority based scheduling. The scheduler for RTOS must support a priority based algorithm with preemption. Priority based algorithms assign each process a priority based on its importance. A process currently running on the CPU will be preempted if a higher priority process becomes available to run. So preemptive priority based scheduler guarantees only soft real-time functionality. It doesn't guarantee hard real-time functionality. So for hard real-time systems, they have to further guarantee or ensure that real-time tasks will be completed within their deadline requirements. Now let's focus on the second feature, that is preemptive kernel. Now you know that non-preemptive kernels disallow preemption of the process running in the kernel mode. The process will run until it either exits the kernel mode, blocks, or voluntarily releases the control of CPU. In contrast, the preemptive kernels allow preemption of process running in kernel mode. So for implementation of hard real-time systems, non-preemptive kernels are not used. Preemptive kernels are mandatory. Now let's see the strategies for making kernel preemptible. So there are two strategies. First one is use of preemption points. Second one is synchronization mechanism. Now let's see the first strategy, that is preemption points. So insert the preemption points in the long duration system calls. A preemption point checks to see if a high priority process needs to be run. If so, the context switch takes place. So the CPU switches from the low priority to the high priority process. When the high priority process terminates, then the interrupted process or the suspended process continues its execution. But the preemption points should be placed at safe locations in the kernel, that is, where kernel data structures are not modified. Now, second strategy for making kernel preemptible is to use synchronization mechanism for processes. With this method, kernel can always be preemptible because any kernel data that is being updated is protected from modification by high priority process because we are using synchronization mechanisms. So the shared data will not be modified by two or more processes simultaneously. Access can be given to only one single process to modify the shared data. For example, here the kernel data is the shared data. Now the third feature that is required for the implementation of RTOS is minimizing latency. Now there are two types of latencies, interrupt latency and dispatch latency. Now let's see the interrupt latency. Interrupt latency refers to the period of time from the arrival of the interrupt at the CPU to the start of the routine, that is interrupt service routine. So if you see here already one process is running. While it's running, an interrupt has occurred. So this module will determine the type of interrupt. After determining the type of interrupt, it will result into context switch. That is, it will suspend the currently executing process and a new process starts executing. That is, new process is nothing but the interrupt service routine. So here the interrupt service routine starts executing. Now the time period between the occurrence of the interrupt and at the time where the interrupt service routine starts executing, that is called as interrupt latency. And for RTOS systems, it is always desired or it is always expected that interrupt latency should be as minimum as possible. So it is crucial for RTOS to minimize interrupt latency to ensure that real-time tasks receive immediate action. As we know that interrupts are disabled when kernel data structures are updated. So RTOS always requires that interrupts are disabled for a very short period of time so that the real-time tasks are immediately taken up for execution. Now let's see the second type of latency, that is dispatch latency. It is the amount of time required by the scheduling dispatcher to stop one process and start another process for execution. So for RTOS, this latency should be minimized so that real-time tasks can be taken up for execution very soon. They need not wait for a longer time. So the most effective technique to keep dispatch latency low is to provide obviously preemptive kernels. Now in this diagram you can see that the event has occurred here. Now what is the event? Event is that the high priority process has entered into the system and has become runnable or needs to be run. Then that is the event. So this is the time interval between the occurrence of that event and the response given to that start of the response to the event, that is called as response interval. Now here this is for processing that event which has occurred through interrupt. Now here dispatch latency has two phases. One is conflict and second one is dispatch. So in conflict there are, if you see, there are two components in this. One is preemption of the process running in the kernel and second one is release by low priority process of all the resources needed by high priority process. So in dispatch phase, the context switch takes place actually from the low priority to the high priority process. If we have three processes, say L, M and H, whose priority is of order L less than M less than H, and H requires resource R which is held by L, then H is waiting for L to relinquish the resource R. But meanwhile, if M enters the system, M has the priority higher than that of L. And if M becomes runnable, then it will preempt the resources from the process L. So H has to wait for M to release the resources R. So this problem is called as priority inversion, which occurs with this system. Now to solve this problem, priority inheritance protocol is used. According to this protocol, all processes that are accessing resources needed by high priority process inherit the high priority until they finish their execution. But when they finish their execution, their priorities revert to the original values. Now, so in the example discussed previously, that is LMH, L temporarily inherits the priority of process H, thereby preventing process M from preempting its execution. Now when L finishes its execution, it relinquishes resource R for H, and its inherited priority from H is reverted back to its original value. So process H will run next but not M. In this way, the problem of priority inversion is solved through priority inheritance protocol. Now let's pause the video, think and write. Identify whether hard or soft real-time scheduling is more appropriate in the following cases. First is thermostat in a household. Second one is control system for a nuclear power plant. Third one is fuel economy system in an automobile. Fourth is landing system in an jet airliner. So if we consider thermostat in a household, appropriate scheduling is soft real time. Reason? A slight delay in turning heating or cooling on or off doesn't cause any catastrophic failure or any disastrous consequences. It only affects comfort slightly. Second one is control system for a nuclear power plant. Appropriate scheduling is hard real time. Reason? Any missing deadline would lead to unsafe conditions, potentially disastrous consequences. So strict timing guarantees are essential here. Fuel economy system in an automobile. Appropriate scheduling is soft real time because missing a deadline may reduce fuel efficiency temporarily but does not pose any immediate threat to passengers' safety. Fourth one, landing system in a jet airliner. Appropriate scheduling is hard real time because delays can cause serious accidents or loss of life. System must meet the timing constraints very strictly here. So these are the references used for preparing these videos. Thank you.